So if you've ever fired up a music visualizer on your computer or, watched one of those really satisfying piano roll videos where the neon blocks fall perfectly onto the keys right as the music swells,
Oh, yeah, those are mesmerizing.
right, you probably assume the software is just, well, listening to the audio. Like you load the track, the computer hears the sound, and it magically draws the colors.
Which is a totally natural assumption to make.
Yeah, but if we actually pull back the curtain on how a machine interprets music,
Mhm.
we find something far more complicated. I mean, usually when we talk about translating something in software, it's a pretty straightforward conversion.
Like swapping Celsius for Fahrenheit.
Exactly. Or translating a string of text from Spanish to English. You have a dictionary, you apply a static formula, and you're done. The inputs and outputs are neatly defined.
Which works beautifully for a closed system where everything is predictable. But translating music into a visual medium, I mean, it completely shatters that predictability.
Because it's not a direct one-to-one mapping.
Right. You're taking temporal invisible pressure waves, or in our case today, dense streams of performance data, and you're forcing them into spatial dimensions, real-time motion, and color palettes.
It's basically the absolute definition of a cross-sensory translation problem.
And the mapping goes way beyond just mathematical complexity. It is incredibly demanding on a computer's physical hardware if you want to maintain, perfect synchronization without the visuals lagging behind the audio.
And that translation problem, that's the exact mission of our deep dive today.
Mhm.
We're looking at the precise mechanics of how software actually listens to music and translates it into those visual equalizers without dropping a single frame.
It's a fascinating challenge.
It really is. And to do this, we're taking a really unique approach. We have a digital artifact from 1998. It's a 16-bit MIDI monitor DLL, a dynamic link library that was originally built by a developer named Eric Rangel for a piece of software called PowerTracks Pro Audio.
Yeah, and that DLL serves as a perfect time capsule of late 90s software engineering. I mean, it reveals the extreme lengths developers had to go to when working with the really constrained processing power of that era.
Right, so we're going to unpack the classic C code that made that 1998 monitor tick, exploring how it intercepted raw MIDI data and painted it directly onto a CRT monitor.
But more importantly, we are going to completely re-architect this 1998 blueprint for the modern era.
Yes, exactly. We're going to explore how an intermediate programmer today can rebuild this robustly in Java, and we'll be putting a massive emphasis on the modern workflow, right? Like using an AI assistant like Claude to vibe code the application step by step.
Which is such a powerful way to work now, but the focus will be on ensuring that the AI-generated code is heavily commented, architecturally sound, and easily readable for that intermediate developer.
So they aren't just blindly copying and pasting.
Exactly. We want to outline exactly how you review that generated code and how you design rigorous unit tests to verify that the application handles extreme exception conditions, like a blistering 500 beat per minute tempo, without crashing or stuttering.
And just to keep our scope tightly focused on that core architectural challenge, we are intentionally ignoring one of the aesthetic features of the original 1998 program.
The history trails.
Right, the original had these history trails that faded out behind the visual notes.
Mhm.
For our modern Java rebuild, we're stripping that away completely.
Which is smart. Maintaining that strict scope is a crucial strategy for an intermediate programmer embarking on an AI-assisted project.
It keeps things manageable.
Yeah, it prevents the AI from hallucinating overly complex UI logic and forces the focus onto the underlying data structures and thread management.
Our singular focus is the engine, right?
Yeah.
Reading a standard MIDI file, playing it back, and displaying real-time color bars in columns.
And once we lock down that foundation, we'll push the boundary even further by integrating cutting-edge audio machine learning.
Making the visuals react not just to raw code, but to the actual expressive acoustic sound. But to appreciate the modern solution, we have to understand the historical problem first.
Let's set the scene.
Picture a beige Windows 95 or 98 desktop computer. You launch your sequencing software, PowerTracks Pro Audio, you load up a complex MIDI arrangement, and you pull up this monitor window. What is the user actually seeing on their screen when this 1998 DLL kicks in?
So the DLL requests a dedicated full-screen window from the operating system. It's running at a resolution of 640 by 480 pixels, featuring a pure black background.
Classic 90s aesthetic.
Oh, absolutely. And across the width of that screen, the software draws 16 distinct vertical columns, which are numbered sequentially 1 through 16 along the bottom edge.
And those 16 columns correspond directly to the 16 channels defined in the standard MIDI protocol, right?
Indeed. Each column acts as an isolated lane for a single MIDI channel. As the sequence plays, individual musical notes manifest as horizontal rectangles or bars inside their respective columns.
So how does the placement work?
Well, the vertical placement of the bar dictates the pitch. A low bass note renders down near the bottom of the monitor, while a piercing high note renders near the top.
Makes sense. And the width of the bar?
Simultaneously, the width of the horizontal bar conveys the velocity. Velocity, in MIDI terms, measures the force with which a key was struck, which basically translates to the volume of that specific note.
So if I hit the key really softly,
A soft, delicate note draws as a narrow bar, whereas a heavily accented note, if you slam the key, it fills the entire width of the column.
and the color scheme wasn't arbitrary either. The source material outlines a color mapping system that is deeply tethered to the general MIDI standard.
Yeah, the elegance of the system lies in its reliance on those general MIDI instrument banks. The DLL utilized a simple text-based configuration file, an INI file, to map these instrument categories to specific RGB hex codes.
Right, so like the general MIDI specification reserves patches 1 through 8 for the piano family.
Exactly. So the INI file instructed the DLL to render any note played by a piano patch in bright red. The strings bank was mapped to pink, synth leads to dark green, bass instruments to purple, and so on.
I can totally see how that creates an incredibly intuitive visual dashboard. You can just glance at the 640 by 480 screen and immediately parse the whole arrangement.
It's instant visual feedback.
Yeah, like if the pink column is swelling with wide bars, the string section is crescendoing. If the purple column is dropping tiny, narrow blocks near the bottom of the screen, you are watching a walking bass line.
The original also featured pitch bend indicators, little moving graphical blips at the bottom of the screen to show when a musician was physically moving the pitch wheel on their synthesizer.
Right. But, okay, buried in the source material is a feature called text mode. And looking at how it was programmed reveals a rather terrifying reality of 90s computing. I mean, I was kind of horrified reading this.
Yeah, text mode is wild.
Yeah.
It was offered as an alternative to the graphical colored bars. Instead of drawing a rectangle whose vertical position represented a C sharp, the software would attempt to render the actual alphanumeric characters.
Like literally the letter C followed by a sharp symbol.
Exactly, directly onto the screen as the note fired.
Which sounds completely reasonable, right?
Right.
Until you read the implementation details.
Right.
Wait, you're telling me they didn't use Arial or Times New Roman or any standard system font provided by Windows?
Nope, they didn't use a system font at all.
The source explicitly states they hand drew the letters pixel by pixel using geometric line commands. That is just, it's insane.
I know, it sounds crazy now. They engineered a custom hard-coded function titled drawchar. Inside this function was an exhaustive matrix of coordinate instructions for every possible letter, number, and accidental symbol required for musical notation.
So they were writing out the X and Y coordinates for everything.
Yes. They relied on primitive Windows Graphics Device Interface, or GDI, commands. The code would literally issue a command to move the cursor to a specific XY pixel coordinate, then issue a line2 command to draw a white line 3 pixels to the right, then another command to draw 2 pixels down.
Oh my God.
They were manually plotting a microscopic 5x7 pixel grid to form the shape of a letter for every single note event.
From the perspective of modern programming, where displaying text takes exactly one line of code, manually plotting the geometric path of a letter C feels like, I don't know, trying to paint a house with a toothbrush.
It's incredibly tedious.
Why would a developer willingly subject themselves to that level of labor instead of just calling a Windows font?
Well, it reveals the severe computational bottlenecks of the era. Rendering a true type font via the Windows GDI is an incredibly heavy operation for a CPU.
Because fonts aren't just pictures, right?
Right. They're complex vector mathematical shapes that must be rasterized, anti-aliased, and scaled to the correct size in real time.
I see.
So if you have a dense orchestral chord playing across 10 different channels simultaneously, asking the 1998 operating system to fetch a font, calculate the vector math for 10 different text strings, and paint them to the screen within a 50-millisecond window.
You would just completely overwhelm the process.
Exactly. The processor would be so busy trying to make the text look pretty that it would forget to listen to the music. The actual audio playback would stutter or crash.
So hand-coding those raw pixel lines bypassed the Windows font engine entirely.
It was an aggressive, brilliant performance hack. It traded days of developer misery typing out thousands of coordinate points for critical milliseconds of CPU cycles during runtime.
Okay, that hustle is genuinely impressive. But if we look at the main loop of the C code, It highlights a structural design that is entirely incompatible with how we build software today. How was the DLL actually acquiring the Midi data from the host sequencer and getting it onto the screen?
So we see a textbook example of a monolithic architecture. The host application, PowerTracks, maintained a circular ring buffer in a shared block of system memory.
A ring buffer is basically an array of a fixed size, right?
Yes, and in this case, it held exactly 1,000 MIDI events. It operates with 2 pointers, a head pointer where the sequencer continuously writes new incoming notes, and a tail pointer where our monitor DLL reads those notes.
And as the head reaches the end of the 1,000 slots, it wraps around back to the beginning, overwriting the oldest data.
Correct.
So our monitor DLL needs to constantly chase that head pointer to read the data before it gets overwritten. How often was it checking?
It relied on a single global Windows timer. Upon initialization, the DLL called the set timer function, requesting an interval of 50 milliseconds.
Okay, so 20 times a second.
Yeah. 20 times a second, the Windows operating system injected a WM-timer message into the application's message queue. The DLL's response to this timer was to invalidate its own window, which forcibly commanded the OS to issue a WM-paint message.
Wait, so it's essentially screaming at the monitor, redraw everything every 50 milliseconds, regardless of whether the music actually changed.
That's exactly what it's doing. And inside the handler for that WMP8 message, the entire application logic executed synchronously.
The whole thing.
The whole thing. The code would grab the graphics context from Windows, then it would look at the ring buffer and drain any pending items. It would parse the raw bytes to determine if a note was turned on or off.
And then draw it immediately.
Right. If a note was turned on, it would instantly calculate the pixel coordinates based on the pitch and velocity, select the correct color brush, and execute the GDI fillrect command to draw the bar. Finally, it would release the graphics context back to the operating system.
Which means reading the raw data, decoding the musical meaning of that data, and physically altering the pixels on the monitor are inextricably bound together in one single uninterrupted breath.
They are completely coupled. The mathematical processing of the music cannot happen unless the operating system is currently allowing the window to paint itself.
I can imagine the fragility of that system. Like, what if the user decides to click and drag the corner of the window to resize it?
Oh, that's a disaster. If you do that, the operating system pauses the WMP and messages to handle the UI interaction.
But while the window is frozen, the sequencer is still pumping notes into that 1,000 event ring buffer.
Yep. The buffer fills up instantly, the head pointer wraps around and begins overwriting unread events.
So by the time the user releases the mouse button and the WM-Paint loop resumes, hundreds of note events have been permanently destroyed.
Exactly. The visualizer will show notes that are missing, or worse, bars that are stuck on the screen forever because the DLL missed the specific note-off command that got overwritten in the buffer.
Furthermore, if I'm a developer trying to maintain this, how do I write a test to ensure my logic for calculating a C major chord is correct?
You really can't.
Right. I can't run a test on the math without also spinning up a Windows graphics environment and simulating a screen refresh. The logic is buried inside the paint routine, so the monolith has to die.
It absolutely has to die.
If our mission is to resurrect this in Java for the modern era, using Claude to vibe code the application, the very first prompt we give the AI needs to address this structural flaw.
Yes. An intermediate developer must instruct Claude to implement a strict 3-layer architecture. We are moving from a synchronous monolith to a decoupled, multi-threaded design.
Okay, what are the layers?
The 3 distinct layers are the MIDI input layer, the state layer, and the render layer. The separation of these concerns is non-negotiable for modern software robustness.
Let's break down the responsibilities of each layer, and specifically, what an intermediate programmer should look for when reviewing the code Claude generates. What is the actual job of the MIDI input layer in our new Java build?
The MIDI input layer has one singular responsibility: catching data. It operates autonomously on a dedicated background thread provided by the Java MIDI subsystem.
Because this is listening.
Just listening. When a hardware keyboard is struck or a MIDI file pushes an event, this layer receives the raw bytes. It wraps those bytes into a standardized Java object and pushes that object onto a concurrent queue.
Okay. Crucially, Claude must not write any logic here that calculates pitch coordinates or interacts with UI components. This layer only catches the event and hands it off to the queue. I like to visualize this using a restaurant analogy. In the 1998 monolithic version, The chef was basically dragging his stove into the dining room, frantically taking the customer's order, cooking the meal directly on their table, and shoving it onto their plate all at the same time.
That sounds incredibly stressful.
Right. But the Midi input layer in our modern version is just the delivery truck arriving at the loading dock. It drops off the raw ingredients, the Midi events, and drives away. It doesn't care what is on the menu.
That analogy perfectly illustrates the decoupling. The delivery truck does not interact with the dining room. It hands the ingredients to the kitchen, which brings us to the second component, the state layer.
The kitchen. So what is Claude generating when we ask for a state layer?
The developer should prompt Claude to generate the state layer as a collection of pure Java classes. This is a mathematical data model representing the absolute truth of the music at any given millisecond.
So it's constantly reading from that queue.
Exactly. It continuously pulls the concurrent queue, pulling off the raw events the input layer dropped off. It then updates its internal tracking variables. It maintains a list of which specific notes are currently active on which of the 16 channels.
Got it.
It tracks the current instrument patch to determine the active color for each column. It stores the current numerical value of the pitch bend wheel. Everything is just data.
And if we look at the import statements at the top of the Java file Claude generates for the state layer, we should not see a single reference to java.graphics or javax.swing.jframe.
Absolutely none. The state layer must be completely ignorant of the fact that a graphical user interface even exists.
Right, it doesn't know what a pixel is.
It does not know the screen resolution. It only knows that channel 4 is currently sustaining a velocity 80A minor chord.
Which leaves the render layer to act as the waiter in our restaurant analogy.
The render layer runs on its own independent loop, typically tied to the refresh rate of the monitor, say, a smooth 60 frames per second. Every 16 milliseconds, the render layer asks the state layer, provide me a snapshot of your current active notes. The state layer passes over the data.
And then the rendering happens.
Right. The render layer then does the math to translate that data into X and Y pixel coordinates, calculates the widths based on velocity, looks up the assigned hex colors, and executes the drawing commands. The waiter takes the fully prepared data from the kitchen and presents it beautifully in the dining room.
This separation completely solves the resizing problem we discussed earlier. If the user clicks and drags the window, freezing the render layer, the background Midi thread and the state layer continue processing the queue in real time.
Yep, the truck keeps delivering, the kitchen keeps cooking.
So when the user releases the window, the render layer simply asks for the current state and draws it. No data was lost. The screen just jumps to the correct current moment in the song.
Beyond preventing dropped data, the most profound advantage of this architecture is testability. This is where vibe coding with Claude becomes exceptionally powerful for an intermediate programmer.
Because you can actually test the logic without opening a window.
Precisely. Because the state layer is a pure data model with zero UI dependencies, you can instruct Claude to generate aggressive, comprehensive unit tests that run entirely in memory.
And this leads us to the critical challenge of testing exception conditions. The source material emphasizes testing the AI-generated code against a blistering 500 beat per minute tempo.
Which is extremely fast.
Right. If we are feeding a frantic, virtuosic piano solo running at 500 BPM into this application, we're talking about thousands of individual node-on and node-off events firing every single second. How does the intermediate programmer use Claude to guarantee the code won't buckle under that pressure?
You prompt Claude to write a JUnit test class specifically targeting the state layer. The test creates a synthetic loop that bombards the process event method with 10,000 Midi messages in a fraction of a second.
Okay, a true stress test.
And then the developer needs to review the AI's implementation against 3 critical failure points that plague real-time audio software. The first failure point is the queue structure itself.
The 1998 version used a fixed 1,000 event ring buffer. If we ask Claude to write the new queue, what specific data structure should we be demanding to handle a 500 BPM barrage?
If Claude generates a standard array list or a fixed-size array, the developer must reject it immediately.
Why is that?
A 500 BPM barrage will easily overflow a fixed buffer between frame renders. Furthermore, because the Midi thread is writing to the queue while the state layer thread is reading from it, a standard list will instantly throw a concurrent modification exception, crashing the entire application.
So we need something better.
The developer must ensure Claude utilizes a robust, unbounded, thread-safe structure.
We'll dig into the specific Java structure for that shortly, but what is the second failure point the unit test needs to verify?
The dreaded stuck note anomaly.
The infinite drone. You stop playing, But one synthesizer key just keeps howling at maximum volume until you forcefully restart the program.
It is the most common bug in MIDI programming. It occurs when a node-on event is successfully processed, but its corresponding node-off event is either dropped from the queue, overwritten, or misrouted due to a logic error in handling complex chords where the same note is struck twice in rapid succession.
How do we test for that?
The developer must instruct Claude to design the unit test to fire 5,000 random node-on events, immediately followed by their exact 5,000 node-off counterparts.
Okay.
The assertion at the end of the test must mathematically verify that the state layer's active notes array is completely empty. If a single element remains, the test fails, alerting the developer that the logic cannot handle dense, rapid-fire polyphony.
And the third failure point during our 500 BPM stress test.
Memory allocation and the Java garbage collector.
Ooh, this is a fascinating architectural trap. Java is a garbage-collected language, meaning the developer doesn't have to manually delete objects from memory like they do in C.
Right, it's supposed to be easier.
The Java virtual machine automatically scans memory and deletes objects that are no longer being used. That sounds convenient, but under extreme stress, it actually becomes a liability, doesn't it?
It becomes a massive liability for real-time rendering. Imagine Claude generates a state layer that instantiates a brand new visual note object using the new keyword every single time a MIDI event arrives.
So at 500 BPM, the application is creating thousands of tiny objects per second.
Exactly. And eventually, the computer's memory starts to fill up with all these dead, used-up note objects from a few seconds ago.
So what happens when it fills up?
When the memory threshold is reached, the Java garbage collector triggers a stop-the-world pause. It literally freezes the entire execution of the program for a few milliseconds to sweep the memory heap and delete the dead objects.
Which means our render layer, which is trying to draw a smooth 60 frames per second, suddenly halts.
Yes, the animation stutters, the visualizer jerks, and the illusion of real-time translation is completely broken.
Therefore, the intermediate developer reviewing the vibe-coded state layer must aggressively hunt for the new keyword inside the main processing loop.
They have to look for it. The AI should be guided to use primitive data types like arrays of integers or booleans to track active notes rather than allocating complex objects on the fly.
Or maybe recycle them.
Exactly. Alternatively, it should implement an object pool, recycling a fixed set of note objects rather than continuously creating and destroying them. Passing the 500 BPM stress test means the memory footprint remains entirely flat from the first note to the 10,000th.
Let's drill down into the specifics of why we are choosing Java for this rebuild. The source material points out that Java is not just a generic arbitrary choice. It actually possesses a highly capable built-in environment tailored specifically for this kind of project.
Java provides a comprehensive toolkit called the javax.sound.midi package. It has been a stable part of the standard Java library for over 2 decades.
Which is a massive advantage for our intermediate programmer. I mean, there is no need to scour GitHub for third-party libraries, compile C bindings, or battle with custom drivers just to get the computer to recognize a USB piano keyboard.
The built-in integration is seamless. The core entry point for the developer is a utility class called Midi system.
Okay, how does that work?
You issue a command to Midi system asking for an array of all connected Midi devices. Once the user selects their keyboard from that list, the code opens the device and requests its transmitter object.
So the transmitter is the hardware throwing the data at us. How do we actually catch it?
You instruct Claude to generate a custom class that implements the Java receiver interface. You then hand an instance of your receiver to the keyboard's transmitter. The routing is established.
Oh, that's simple.
Very simple. From that moment forward, every time a physical key is depressed, the Java subsystem automatically invokes the send method inside your receiver class, passing in a MIDI message object.
It is incredibly clean. But this brings us back to the most critical architectural bridge we discussed earlier. The Java subsystem is invoking that send method on a hidden background OS thread. But our render layer is forced to draw the graphics on the main UI thread.
Right, the classic problem.
We have our truck dropping off data and our waiter trying to serve it, and they are operating in 2 entirely different parallel timelines.
This is the classic producer-consumer concurrency problem, and it is exactly where amateur applications crash. The background MIDI thread is the producer. It is aggressively throwing objects at our state layer.
And the UI thread is the consumer.
Yes, the main UI thread, which in Java Swing is called the Event Dispatch thread, or EDT, is the consumer, attempting to read that state layer to draw the frame.
We mentioned earlier that a standard array would cause a concurrent modification exception if both threads touch it simultaneously. What specific Java structure should our developer demand Claude use to build the queue?
The prompt must explicitly require a concurrent linked queue.
Why that specific class? What makes it immune to the crashing?
The concurrent linked queue is a lock-free, thread-safe data structure designed precisely for high-throughput, multi-threaded scenarios. When a standard list is accessed by two threads, developers usually have to use a synchronized lock.
Meaning what exactly?
It means the background thread literally locks the door to the list, writes the data, and unlocks the door. If the UI thread tries to read the list while the door is locked, it is forced to wait.
And in a 500 BPM scenario, forcing the UI thread to wait for a lock means dropping visual frames.
Exactly the problem. The concurrent linked queue avoids traditional locking by utilizing low-level atomic compare and swap hardware instructions. It allows the background Midi thread to push data into the queue at maximum velocity without ever blocking or locking the UI thread.
So the background thread is just stacking boxes on a conveyor belt as fast as it can. How does the UI thread, the event dispatch thread, actually consume those boxes to trigger a screen refresh?
The developer instructs Claude to instantiate a javax.swing.timer. This timer is native to the event dispatch thread. It's configured to fire every 16 milliseconds, aligning with a 60 frame per second monitor refresh rate.
And when timer wakes up?
When it wakes up, it executes a loop that pulls the concurrent linked queue. It drains every single MIDI message that is piled up on the conveyor belt since the last frame, passes them to the state layer to update the active notes, and finally issues a call to repaint.
Repaint being the modern Java equivalent to the 1998 WMP command we discussed earlier.
Correct. It signals to the Java graphics engine that the underlying data has changed, and the window must be drawn fresh on the next cycle.
But consider the actual drawing process. In 1998, the CPU was manually calculating the math to alter individual pixel colors in the system memory. If we're asking Java to draw 16 wide columns, potentially dozens of actively moving colored bars representing dense chords, updating dynamic text labels, and sliding pitch bend indicators.
It's a lot of math.
And we are demanding it do this 60 times every single second. Does the modern CPU not suffer the same bottleneck? Does the math not overwhelm the processor?
The math is indeed staggering, but the modern CPU does not handle it. This is where the sheer power of the Java 2D API shines, completely abstracted from the developer's view.
How so?
Well, if our intermediate programmer reads the rendering logic generated by Claude, it appears deceptively simple. They will see high-level commands like graphics2d.setColor, color.red, followed by graphics2d.fillRect xy width height. It looks structurally similar to the primitive 1998 C commands.
But the underlying execution is fundamentally different.
Completely different. Java 2D implements an automatic hardware acceleration pipeline. When the program calls fillRect, the Java virtual machine intercepts that command.
It doesn't send it to the CPU.
No, instead of forcing the computer CPU to calculate the pixel matrix, the JVM translates the command into native graphics instructions, Direct3D on a Windows machine, or Metal and OpenGL on a Mac. It passes the heavy mathematical lifting directly to the system's graphics processing unit, the GPU.
Oh, well. The graphics card is specifically designed to perform thousands of parallel mathematical operations simultaneously.
Precisely. So rendering those 16 columns of dynamically resizing color bars, which would choke a 1998 CPU, requires virtually zero effort from a modern GPU. The UI thread remains incredibly lightweight, ensuring the 60 frames per second animation remains buttery smooth, regardless of how dense the MIDI arrangement becomes.
From a developer's perspective, everything we have discussed makes Java sound like a paradise. You get the built-in MIDI package, you get the lock-free concurrent queues to handle extreme tempos without crashing, and you get automatic GPU hardware acceleration without having to write complex shader code.
It's a very robust tool set.
But I have to push back on the user experience. If I build this amazing visualizer in Java and I want to share it with a non-technical friend, do I have to send them a link to Oracle's website?
Ah, I see where you're going with this.
Like, do they have to manually download a clunky Java runtime environment, figure out how to set their system path variables, and endure those infamous system tray updater pop-ups just to run my program? Because if so, users will simply refuse to try it. That distribution model feels trapped in 2005.
You're completely right. The friction of requiring a system-wide JRE installation was a massive detriment to Java desktop development for a very long time. It alienated end users. However, The modern Java ecosystem has entirely eradicated that problem, which is another reason it is recommended in the source material.
Okay, so how does an intermediate programmer bypass the JRE requirement?
They utilize a packaging tool introduced in Java 14 called JPackage. You do not just compile your code into a .jar file and email it to your friend anymore. Instead, you run your compiled application through the JPackage utility.
What is the utility actually doing under the hood?
It employs a process called modular linking. It analyzes your application and identifies exactly which specific modules of the Java runtime your code actually uses, for instance, the Java.desktop module for the UI and the Java.sound module for the Midi input.
And it just ignores the rest.
Exactly. It discards the rest of the massive Java library. It then bundles your application code together with this microscopic, custom-tailored Java runtime and wraps the entire package into a native operating system installer.
Oh, so it generates a standard .exe or .noci file for Windows users.
A standard executable for Windows, a .dmg file for macOS, or a .deb package for Linux.
That's amazing.
When your friend downloads the file and double-clicks it, it installs and runs exactly like a native C++ or Swift application. The user remains completely oblivious to the fact that it is a Java application. There are no prompts to install external dependencies. The deployment friction is completely eliminated.
That dramatically shifts the viability of Java for modern desktop software. But to ensure we are looking at the complete picture provided by the source material, we should briefly contrast this Java pathway with the alternative ecosystems that were considered.
Sure, it's good to know the options.
The notes specifically outline the potential of building this visualizer in a web browser, or building it natively in Rust. Let's explore the trade-offs. What if our developer decided to ignore Java and ask Claude to vibe code this as a web application using TypeScript?
A browser-based approach offers the ultimate frictionless distribution. You do not even need an installer. You host the code on a server, send the user a URL, they click the link, and the visualizer is instantly running on their screen.
Right.
The developer would utilize the Web Midi API to capture the keyboard input and rely on the HTML5 Canvas API to render the colored columns.
Instant distribution and universal access. Why wouldn't that be the default choice for this project?
Well, the browser environment imposes two severe penalties for real-time audiovisual translation. The first penalty is architectural latency.
How bad is the latency?
When you instruct an HTML5 canvas to draw a rectangle, the browser does not communicate directly with the monitor. It routes that instruction through a massive, complex rendering pipeline, eventually handing it off to a browser compositor thread.
So it's not immediate.
Right. Even if your JavaScript code processes the Midi event in 1 millisecond, the browser's compositor might add an artificial delay of 10 to 30 milliseconds before the pixel physically changes color on the glass.
30 milliseconds might not sound like much, but human perception is incredibly sensitive to audio-visual desynchronization. If a musician strikes a key on their MIDI controller and the sound hits their ear, but the visual bar appears on the screen 30 milliseconds later, it feels disconnected, it feels mushy.
The immediacy of the physical interaction is ruined. The second penalty involves restrictive platform support caused by security protocols. Web Midi requires the browser to open a direct communication channel with the computer's low-level hardware ports.
And Apple doesn't like that.
No, Apple has deemed this a severe security vulnerability, fearing malicious websites could use hardware access to fingerprint devices. Consequently, Apple's Safari browser explicitly blocks the Web Midi API entirely.
So your frictionless web application simply will not function for any user on an iPhone, an iPad, or anyone using the default browser on a Mac. That is a massive demographic to lose.
Exactly.
Okay, consider the opposite end of the spectrum. What if our intermediate developer wants absolute, uncompromised performance and decides to build the visualizer in Rust?
Rust represents the pinnacle of modern high-performance systems programming. If you write this in Rust, you gain direct, low-level access to the operating system's native MIDI drivers.
So zero latency.
There is no browser compositor thread adding latency, and there is no Java virtual machine sitting between your code and the hardware. You achieve the absolute lowest possible latency.
And for the graphics, the source material mentions a library called the WGPU.
Yes. Rust, combined with the WGPU framework, allows you to bypass CPU drawing routines entirely. You can write custom shaders code that executes directly on the cores of the graphics card. You command the GPU exactly how to calculate the pixel colors for the 16 columns without any abstraction layers.
If Rust provides zero latency and limitless GPU power, why does the source material ultimately recommend Java as the sweet spot for our intermediate developer?
Because of the cognitive load required to write and maintain the code. Rust enforces memory safety through a mechanism known as the borrow checker.
I've heard that could be tough.
It is notoriously strict and mathematically proves that your memory access is safe at compile time. For an intermediate programmer trying to vibe code a multi-threaded producer-consumer queue, fighting the Rust borrow checker can be a frustrating, deeply complex experience.
So it slows down development.
Yes. Furthermore, setting up the boilerplate code required to initialize a WGP rendering pipeline requires hundreds of lines of obscure configuration before you can even draw a single colored square.
It is the difference between driving a reliable automatic transmission and trying to build a Formula One engine from scratch.
That's a great way to put it.
Java strikes the pragmatic balance. It offers familiar, readable, object-oriented code that Claude can generate reliably. It provides the thread-safe concurrent queues necessary to survive a 500 BPM stress test. It abstracts the complex GPU math behind simple fill-rect commands, and it packages into a native executable without external C bindings.
It allows the developer to focus entirely on the logic of the visual translation rather than fighting the environment.
So we have successfully modernized the 1998 monolith. We have our decoupled, heavily tested, concurrent Java architecture confidently rendering our 16 columns of Midi data. But everything we've discussed so far is merely visualizing a digital blueprint.
Right, the Midi data itself.
The source material outlines a fascinating final frontier for this project, supercharging the visuals by moving beyond raw Midi and integrating actual audio analysis and machine learning.
This represents a profound shift in how the software interprets the performance. Up to this point, the application has only been visualizing the intent of the musician. A Midi file is essentially digital sheet music.
It's an instruction set.
Exactly. It's an instruction set that states, strike the C4 key on channel 1 with a velocity of 80.
But the instruction set possesses no awareness of what the resulting sound actually is. To borrow our earlier analogy, Midi is the recipe. The audio is the actual baked cake.
I like that.
The recipe tells you to press the keys, but it doesn't know if those keys are triggering a massive, echoing grand piano in a concert hall or a cheap, thin synthesizer patch through a distortion pedal.
And the visualizer currently draws the exact same pink rectangle for the C chord regardless of the acoustic texture. To bridge this gap, the developer must synchronize the Midi playback with the actual audio output and perform a mathematical operation on the audio waveform called a short-time Fourier transform, or STFT.
I've seen that term used in audio processing. How does an STFT actually allow the visualizer to listen to the texture of the sound?
Imagine holding a complex blended fruit smoothie. You know it tastes like fruit, but you cannot easily determine the exact ratio of strawberries to bananas. A Fourier transform is a mathematical algorithm that unblends the smoothie.
That's a helpful way to think about it.
It takes a tiny time slice of a complex audio waveform, a soup of overlapping sound waves, and mathematically separates it into its constituent frequency components.
It sorts the sound into separate buckets based on pitch.
Exactly. It outputs an array of frequency bins, detailing precisely how much acoustic energy is present at 440 Hz, 880 Hz, 1000 Hz, and so on. Because our state layer already knows the mathematical pitch of the active Midi notes, the render layer can look up the corresponding frequency bin in the STFT data.
So instead of the width of our colored bar being permanently locked to the static Midi-velocity number from the recipe,
The width of the bar dynamically expands and contracts based on the actual physical acoustic energy radiating into the room. The visualizer transcends code and reacts at the physical resonance. If a piano player holds the sustain pedal, allowing a chord to ring out and slowly decay, the drawn bars will visually pulse and slowly shrink in real time, mirroring the fading sound waves. If a vibrating string triggers sympathetic resonance in an adjacent string, the visualizer will flutter, displaying acoustic phenomena that the Midi file never explicitly commanded.
that elevates the visualizer from a mere dashboard into an organic breathing reflection of the music. But I see an immediate complication.
What's that?
If I am listening to a dense, fully produced track pounding drums, a walking bass line, sweeping string chords, and a vocal melody, the audio waveform is a chaotic collision of frequencies. How does the application perform an STFT and know which slice of acoustic energy belongs to the purple bass column and which slice belongs to the pink string column? The Fourier transform just sees one giant wall of sound.
That complication is the precise reason the source material introduces deep learning source separation. The developer integrates tools like Demex or Spleeter into the audio pipeline.
I am familiar with the concept of those tools. They are AI models that isolate stems, correct?
They are neural networks trained on vast libraries of multi-track studio recordings. They utilize complex architectures, like UNITs, to recognize the distinct harmonic fingerprints of different instruments within a flattened audio mix.
And they can do this in real time.
Yes. Instead of analyzing a messy, combined waveform, the application routes the master audio through the Demix model in real time. The model mathematically slices the audio into isolated, distinct stems, a pure drum track, a pure bass track, a pure melody track.
And we route those isolated stems into our visual architecture.
Precisely. The render layer no longer runs a single STFT on the master mix. It runs concurrent STFTs on the isolated stems. The purple bass column on the screen is strictly analyzing the acoustic energy of the isolated bass audio.
And the red piano column is analyzing the pure piano stem.
Yes. The color, brightness, and width of each of our 16 columns are now driven by mathematically purified acoustic energy, completely unpolluted by the frequencies of the other instruments.
The fidelity of that translation is incredible. We're using neural networks to clean the audio before we visualize it. But the source material suggests one final, incredibly sophisticated application of machine learning. It discusses using AI not just to separate the audio, but to hallucinate missing data. Why would we need to invent data that isn't there?
It addresses a fundamental flaw in the vast majority of MIDI files available today. Most MIDI sequences are heavily quantized and programmed with a mouse on a grid.
So they're very rigid.
They contain the basic note-on and note-off commands, but they completely lack the continuous expressive metadata that a human musician provides. They lack the subtle, gradual movements of the modulation wheel, the delicate writing of a volume expression pedal, or the dynamic sweeping of a synthesizer filter.
The resulting playback sounds sterile.
Yeah.
It sounds robotic because the human micro-expressions are missing.
The AI can restore that human soul. The developer can deploy a machine learning model that has been trained on a massive repository called the Maestro dataset.
What's the Maestro dataset?
It contains over 170 hours of virtuosic piano performances, where the pristine acoustic audio is perfectly aligned with the high-resolution MIDI data capturing every micro-movement of the pedals and keys.
Oh, I see. By studying that dataset, the neural network learns the correlation between the nuances of the acoustic sound waves and the physical controller movements that produce them.
The model learns how a human breathes with the music. The visualizer application can feed the sterile, robotic MIDI playback into this trained model.
And what does the model do with it?
The AI listens to the chord progression and dynamically infers the missing expressive data. It mathematically deduces, based on the harmonic tension of this crescendo, a human performer would be aggressively pushing the expression pedal right now.
It generates that continuous control change data, the CC data, in real time.
It hallucinates the missing human intent and feeds that generated data directly into our state layer. Consequently, the user interface comes alive.
That's amazing.
The tiny UI elements tracking volume, panning, and modulation begin to animate autonomously, dynamically sliding and sweeping. The visualizer reflects a deeply expressive, emotionally resonant human performance, generated entirely by the AI analyzing the static code.
It completely bridges the gap between deterministic software and acoustic reality. We have journeyed an incredibly long way today. We began by dissecting a 1998 C language monolith, where the software was forced to manually draw a text pixel by pixel, and where reading a memory buffer and updating a monitor were suffocating each other in a single synchronous loop.
We saw how an intermediate developer could break that monolith apart, employing Claude to vibe code a modern 3-layer Java architecture.
Yeah, we explored the critical necessity of using lock-free concurrent queues to prevent thread collisions, and the importance of stringent unit testing to ensure the application processes 500 beat per minute tempos without triggering catastrophic garbage collection pauses.
We leveraged modern tools like JPackage to eliminate distribution friction, and hardware-accelerated Java 2D to effortlessly render 16 dynamic columns.
And finally, we plugged neural networks into the pipeline, utilizing Fourier transforms and source separation to map actual breathing acoustic energy onto our screens, even hallucinating the missing human soul of the performance.
It serves as a masterclass in how architectural patterns have evolved to prioritize testability and multi-threading, while simultaneously highlighting how machine learning is fundamentally shifting our software from executing rigid instructions to possessing contextual sensory awareness.
Which leaves us with a profound inversion of the entire process to think about. We have spent the last hour exploring how to build software that perfectly translates an audio performance into an expressive visual dashboard. But if a neural network can analyze audio and hallucinate the precise mechanical data required to draw moving colors and shapes, Could this system be run in reverse?
Reversing the sensory mapping.
Imagine feeding a future iteration of this model, a silent, chaotic video file, a time-lapse of a sunset over a bustling city, or the frantic movement of a flock of birds. Could the AI interpret that visual motion, map the changing colors and shapes into our structural state layer, and hallucinate a perfectly expressive, deeply emotional MIDI piano performance to match the visual tension? The dictionary of translation is no longer constrained to a single direction. We are no longer just teaching computers to see the music. We are on the verge of teaching them to hear the visual world. Something for you to ponder the next time you watch a simple column of color dance across your screen.